So
You should try.
yes, this week we now have no visitors for the first time, maybe for after many months. So Linda will talk about people find something, right?
Yeah,
Yeah.
so it's about dichromatic number. We had struggled a lot to title it, so
All right.
but it's about excluding certain orientations of people and then getting a bound on the dichromatic number of a digraph. This work is all a little over a year old, which is related to the fact that we have had a ton of visitors at IBS. But it's good for me to talk about it now because we just finished the revisions on the paper. So this is all joint work with Tomasz Mazarzik, Marcin Pilipczuk, Amadeus Reinhold, and Weberton Sousa. Amadeus was an intern at IBS while we were working on this. So first, I will give you some disclaimers that I try to be nice to people, but like this talk is really about the induced subgraph and induced subdigraph relation. So I will likely use the word contains to mean contains as an induced subgraph or as an induced subdigraph. And I'll also say something is F-free if it doesn't contain it as an induced subgraph or induced subdigraph. And same thing for the set of edges. And if you need to stop me at any moment to clarify, I'm happy to do that. I just have learned from experience it's best to warn people ahead of time because I'm incapable of saying contains as an induced subgraph. So the other point about this talk is maybe like 30 minutes into the talk, like the beginning of the talk should be very non-technical, and then it will be a more talk only for people who care about knowing about the proof. So maybe some of the less structurally oriented people will want to fall asleep then or leave. So anyway, on to the actual talk. So I'm going to start off by talking a bit about induced subgraphs and chromatic number, which is kind of the motivation for this. Again, we call it class of graphs. We say they're bounded chromatic number if they are all C colorable for some constant C, not super surprising definition. And so we really want to know what are the induced subgraph abstractions to a bounded chromatic number. So clearly you have to exclude a clique because otherwise you contain every clique and cliques have arbitrarily large chromatic number. But can this somehow be the complete story? This is perhaps less immediately clear. But in fact it can't be. So this is a famous result of Erdős, maybe the first use of the probabilistic method, that there exist graphs with arbitrarily high girth and arbitrarily high chromatic number. So in particular, if your set F does not contain a forest, then the set of F-free graphs cannot have bounded chromatic number. Which led to the following conjecture proposed independently by András Gyárfás and Sumner in the late 70s, early 80s respectively, that if you, whatever clique you exclude and whatever forest you exclude, you end up with a set with bounded chromatic number. And that's, we know they have to contain these two, so and all minimal sets that bound their chromatic number that are finite will have this form, so it's just asking if there's this full characterization, and that's still very open in general. And so we wanted to know a similar thing for digraphs, if we can come up with some characterization of what are the obstructions in terms of induced subdigraphs for chromatic number and coloring of digraphs. So the first notion you could think of is maybe saying, okay, like if we take an overrightarrow graph F, we'll say a graph doesn't contain it if we can somehow direct the edges in such a way that it doesn't contain that as a induced oriented graph. So yeah, I'm not sure that's a super clear notion. So that gives us this stronger version of the Gyarfas-Sumner conjecture that we can say for every forest and integer k, there's a constant C such that all graphs that don't contain this forest F in the sense that they can be oriented in such a way that they don't contain F, and clique number at most K are C colorable. Another way of wording this would be for every oriented graph that does not contain F and doesn't have a clique of size K, its underlying graph has bounded chromatic number. And that's like super false. So it's false even for P4, which if you know about the chromatic number case for regular graph paths, P4 is a very trivial case. And paths in general are easy to prove. So it was shown to be P4 for the directed path, so all edges going the same orientation by Kierstead and Trotter. They showed that Zykhov's construction can be oriented in such a way that it avoids this, and the alternating orientation of P4 was shown to not bound the chromatic number by looking at shift graphs by and that was shown by Gyarfas. So the question was whether or not the other two orientations are. It turns out they work. This is a super non-trivial theorem. So if you have the orientation where these appear to be, I think there's a typo in these. I mean these two, they should be this one and this one. Yeah, so these so it's the orientation of P4 that is neither the directed P4 nor the alternating P4. And those actually do, excluding those, bounds the chromatic number of the underlying graph for any oriented graph. And that's also true for any orientation of a star. And these bounds are like super polynomial, and like they're maybe like doubly exponential. They're very fast growing bounds in terms of the clique number. So we kind of give up on that because, well, one, it doesn't really seem to work for most cases, and there's very few open cases left after we've said that directed P4s and oriented P4s don't work. So we're going to instead use something called the dichromatic number, which was defined by Norman Lara, and then subsequently popularized by Erdős. And basically it means that you divide into color classes where every color class has no directed cycle, and the dichromatic number is the minimum colors you need for such a coloring. And that's fairly standard by now, I think. At least I see a ton of papers on it. I learned it in my undergraduate graph theory course, so I think it's the most standard, but it has since been brought to my attention that it's maybe not quite so standard as to be the only notion of coloring for digraphs. So for the case of tournaments, we know everything. So we call, say, a tournament K is a hero if all K-free tournaments have bounded dichromatic number. And there's this lovely theorem by Ellie Berger and many other people that gives a full characterization of heroes. It's a simple recursive statement. I thought I would tell it to you just for fun, but I don't feel like writing it out. But you can see it's like, this is the part of my notes that says it. So if you really want to know, you can ask me after the talk. The point of this talk is that it's short. So we care more about what happens in general digraphs. So we know what happens for tournaments. What about just the class of all digraphs? So we call a set F heroic if the set of F-free digraphs are C dicolorable for some constant C. And clearly, if it's heroic, it has to contain some tournament. Otherwise, F-free digraphs contain the class of all tournaments, which can have arbitrarily high dichromatic number. And also, it has to contain some clique where every edge is a digon. A digon is this directed cycle of length 2. So if you don't contain that, you could contain arbitrarily large cliques where every edge is a digon, and those will have also unbounded dichromatic number, because if every edge is a digon, dichromatic number and chromatic number are actually the same. Anyway, so in this talk we're looking at what are the minimal heroic sets. And so again, as I've mentioned many times, there's this lovely theorem of Erdős that you can have graphs with arbitrarily high girth and arbitrarily high chromatic number. More surprisingly, there's a similar theorem for dichromatic number in directed cycles. And so there are digraphs with no directed cycle of length at most k and arbitrarily high dichromatic number. And this is so this is like a theorem that I was asked on my qualifying exam. This is one that would be really rude if somebody asked it to you on your qualifying exam. Like, it's not, this is using really hard probability theory and some like pre-existing results that were also hard. If you want to know more about the proof, I would like to redirect that question to the EchoPro group. So anyway, we take this as a black box. So it was observed by Aboulker, Charbit, and Naserasr that, okay, so if you have a finite set of digraphs and it's heroic, well, it has to contain a forest, because otherwise you're in trouble because of this theorem. Yeah, sorry, this should say forest where every edge is a digon, because otherwise you can look at just take any one of these graphs and replace every edge with a digon and you get in trouble. And it has to contain a oriented forest because of this result. It has to contain a clique where every edge is a digon, because again, then you get, as I mentioned before, cliques where every edge is a digon have arbitrarily high chromatic numbers, so you have to somehow kill them, and it has to contain some tournament, which is a oriented clique, because again, tournaments have arbitrarily high dichromatic number. And so based on this is just repeating the same thing. They kind of were thinking about what could be the minimal heroic sets, so this immediately gives you that the only heroic set of cardinality 2 is the digon and a single edge. And also, every heroic set of size 3 has to either contain the complement of a clique, so just a stable set as an induced subgraph, so it has a bound on the maximum size of a stable set, a digon, and just an arc. And so if we're excluding the digon, then this is equivalent to the graph case, because we're saying that any pair of vertices are either non-adjacent, or they have, sorry, not a digon, an arc, or they have a digon going between them, so then it's the same as graphs and dichromatic number. So this, we already have the Gyarfas-Sumner conjecture, and people are working on it. When we exclude the complement of a clique, then that's fully characterized and known. So the only remaining case that is not Gyarfas-Sumner conjecture is when we forbid a digon, and this we call oriented graphs.
By only remaining, you mean to characterize heroic set of size 3,
yes,
right?
Yes, you can still ask questions about larger sets. Yes.
I see.
But yeah, heroic sets of size 3 are the first interesting case. And again, because of this, somehow you would expect large heroic sets may be a bit uninteresting. Okay, so, and they also showed in the same paper that if you have a heroic set of size 3 containing a digon, then the other elements, one of them has to be an oriented forest, and the other one has to be a hero, where, remember, a hero is this tournament for which all tournaments not containing it have bounded dichromatic number. And additionally, either that tournament you're excluding has to be transitive, or the oriented forest is the disjoint union of oriented stars. Actually, yeah, I'll give you a second because it's a little hard to parse. And so based on this, they conjectured that the converse holds. But that turns out to be false. So I can maybe draw one of the counterexamples. But basically, they demonstrated that there's some sets that are a digon, a tournament, which I'll define, and disjoint union of oriented stars. So maybe some directions. This is just an example, where this is not heroic. However, K is a hero for tournaments. So one possible K is so I'm skipping some. So this tournament, which is a little hard to see, but basically the point is that they have counterexamples on 6 vertices, and they have 4 of them.
What is K transitive? K is transitive.
No, is transitive or.
Or.
Yeah.
Uh-huh.
So it is true. So
Okay.
in the case where it's non-transitive, there are tournaments which are heroes for tournaments, but excluding that tournament and the disjoint union of oriented stars and a digon doesn't work for general digraphs. And the way they did this was actually they looked at complete oriented multivariate graphs and looked at the tournaments of these, and they've more or less fully characterized them, and it turns out to be a more restrictive class than all heroes for tournaments. But as you mentioned, it is still totally possible this conjecture holds when we just look at the K-transitive case, and that's actually the subject of this talk. And just as a remark, I think everyone knows this, but sufficiently large tournaments will have a large transitive subtournament. So saying that you're excluding a transitive tournament is the same thing as saying that the tournaments are all of bounded size. Yeah, just to summarize, I think we have, so these results we saw already, that if you're excluding some transitive tournament K and a oriented force F, then by this result of Twardowski, Scott, and Seymour I mentioned earlier, you will have bounded chromatic number in your oriented graph, so not even caring about dichromatic number, and you won't if your choice of F is the directed P4 or the alternating P4. So for the bounded dichromatic case, which is what we're interested in this talk, clearly since chromatic number is a lower bound for dichromatic number, upper bound, one of the two, these 3 immediately hold. And then in the meantime, we had some initial results that, like, if you exclude directed P4 and you don't have tournaments of size at most 4, then you have a bound on the dichromatic number. And Gyarfas-Sumner also showed that if you exclude the alternating P4 and a cyclic triangle, then you have dichromatic number at most 2. So we had some initial results. And then the last 2 orientations, we just showed bound the dichromatic number in terms of the size of the largest tournament. Since we put the result on archive, but not related notes independent of our result, like they had more or less already had it by the time we had the result. Aboulker, Arbin, Charbit, and Thomasay showed that if you have a directed P6 and no 3 vertex tournament, then you have dichromatic number at most 382, which is kind of the state of the art for this conjecture. There's also a few more results by Carpomero, Hump, Moore, and Spurkle that are a bit related, but not related enough that I didn't include it on this slide. But if you're interested in a subject, it's worth taking a look at their paper as well. And so, yeah, now this would be, I guess I can have a break for questions, but this would be like the end of the non-technical portion of the talk.
So is your theorem implied by the P6 thing?
No,
You don't
no.
care about...
No, not at all. I don't. Somehow I ended up back at the beginning.
Yours is P4 and theirs is P6?
Yes, but theirs is P6 for only 3 vertex tournaments, and ours is for any size of a tournament. So
I see.
neither our result does not imply their result does not imply our result.
I see.
That's also, yeah. There was a funny thing where we were originally told by like a third party that they had proved it for directed P6 for any size of a tournament, and then we were very sad because we were like, oh no,
Okay.
they beat us by a lot. But then we emailed them and we're like, oh, we have this result, we heard you're working on something similar, and then they're like, oh yeah, just for triangle free case, and we're like, okay, that's great, we can keep.
When you say no 3 vertex tournament, do you mean no 3 vertex transitive tournament? Or
No,
any
just
tournament?
no tournament on 3 vertices.
Oh, no
so
tournament,
like
I see.
it's really triangle free.
I see.
Yeah. So yeah, I'm done with the slides.
You need to start the board talk, right?
Yeah. Yeah, this is also, I mean, I was being somewhat serious that if you're in the ECHO program, you might want to leave at this
Wow,
point.
you can enjoy. Oh, there's a switch
Don't
over.
cite me quote me on that out of context.
Oh, that's the wrong switch actually. That's the switch for the camera? Or I don't know.
It's for the.
Yeah, okay.
You may start.
Okay. So I was going to prove the P4 directed P4 free case on the board. All cases, also the alternating case, and it works for all orientation of P4 pretty similarly. But for whatever reason, people like the directed P4 best. So I prove it for that one, and actually the other cases are slightly simpler. So first I'm going to kind of highlight the 2 main tools we have. So the first thing is something that we call a dipolar set. Or so we call a set dipolar if every vertex either doesn't have any in neighbors coming into it from the rest of the graph, or it doesn't have any out neighbors coming into it on the rest of the graph. So in picture form, like if this is your digraph and here's your dipolar set, you can't have a vertex that has something like this happening. And the reason we call it dipole is it's kind of like a magnet, there's 2 poles. And so there's a rather easy lemma that stated here and proved in the next board. If these oriented graph, so for the rest of the talk I'm always going to be assuming there's no diagon. And for all D prime, so induced sub-digraph of D, has a dipolar set with bounded dichromatic number, then the whole thing then the dichromatic number of the thing itself is at most twice that bound. And this I should mention is a result of Aboulker, Charbit, and Naserasr. So
if you have a set of single vertex, then that's dipolar, right? Oh no, sorry.
yeah.
I'm trying to count examples but anyway.
Yeah.
So the statement says that it's enough to have one dipolar set in any D
In
prime.
in every D prime has to have one.
I
But
see. Okay.
yeah, just one. And I mean, it looks like it might be a hard statement. The proof is actually quite easy. So you take a minimal counterexample. And let S B of D be a dipolar set. And then by definition we can partition S so that one set doesn't have any out neighbors in the graph outside of S, and the other part of S doesn't have any in neighbors in the graph outside of S. And then we just do the following coloring. So actually use some colors. So if this is your digraph D, and we have S here, well, by induction we can color this with two gamma colors. And then we partition S into S prime and S prime prime. And again, since the whole of S had a dichromatic number at most gamma, we can color each of these with gamma colors, but we're going to use different palettes of colors. So we're going to use one set of gamma colors for this, and one set of gamma colors for that. So we partition this 2 gamma into 2 palettes, and that is already a dicolor because diagram of colors. Because if you had a directed cycle and it's entirely in here, you know you're good because this is a proper dicoloring, and same thing for any of these sets. And since these don't have out neighbors, they only have in neighbors, and these can only have out neighbors. If you have some dicoloring that's using a vertex of S and a vertex that's not in S, it has to contain a vertex of both S prime and S double prime. And since we use different colors for S prime and S double prime, there's no monochromatic directed cycle. And this, thus far, seems to be the main tool in these kind of proofs that sort of, I guess, in chi-boundedness, maybe you look for things like clique cut sets. Here you look for a dipolar set where you can bound the dichromatic number and win that way. I believe, well, I know the P6 result also uses a dipolar set, and ours does heavily, as did the previous triangle-free P4 free result. I didn't read the cyclic triangle-free alternating path free result, so I don't know what Raphael did. Optimize. So we really need the proof for the future. So going to define, or let's call it find a dipolar set in P4 free oriented graph. And to do that, we need to introduce a few definitions, but they're not too bad. So the first is we call something a closed tournament if you can get it from a tournament and you add a minimum set of vertices to that tournament in order to make the whole thing transitive. So it's equivalent to saying you have a tournament and you take a shortest path from a sink component to a source component.
Can you repeat?
I'm going to write it down.
Yeah, okay.
Yeah.
Did you mean that D prime is dipolar? It has dichromatic number at most y or gamma? Is this?
No, this is a statement about D.
Oh,
I want it because D prime. So if D has the property that for every
I think the confusion is that there is not a full sentence there. D has a dipolar set S and D, so D prime has a
dipolar.
So that's a
and
subset of D prime.
D prime has dichromatic number at most y.
No,
Oh,
this
no.
should be D.
Yeah. Then,
There's no prime here.
ah,
I mean, it doesn't matter because D
All right.
prime is an arbitrary induced subgroup.
okay, and then you should probably also say the dichromatic number of D is at most. What?
Hmm?
No.
I don't.
So the dipolar set itself induces a graph of dichromatic number at most gamma. And that y is actually gamma.
Okay.
No, but the set is a subset of D prime. Is it a
Okay,
subset
yeah,
of D
so
prime?
D prime.
No.
D prime is an induced.
Yeah,
D prime is arbitrary graph, so you don't
let
know.
me maybe rewrite it more carefully.
So any D prime has a dipolar set which induces a sub-digraph whose dichromatic number is at most gamma. That's the condition.
And that S is a D induced on S. D prime is.
Yes, but I should mention now for the duration of this talk, since the only containment relation is into subgraph, I will be, for dichromatic number, the dichromatic number of a set of vertices is the dichromatic number of the digraph induced by it, otherwise it gets hard. Yeah, no, sorry, I should have introduced the sets as
Yeah.
subgraphs thing. Thanks for the clarification. So yeah. So a closed tournament is the union of a tournament and a directed path from a sync in the tournament to a source tournament in sync. K. So that's a closed tournament. Is K union VP, so it's a union of a path and a tournament where you have a path from a sync component to a source component, and it's and its minimum if it minimizes the number of vertices in P. And so for the only time in our talk, P is really not necessarily an induced path. It's just any directed path.
What do you mean by sync compound? What is
Probably strong component, right?
Yeah, so we're looking at the strongly connected components of the tournament.
But-
And
But what confuses me is a path in the tournament from a sync component to a source
no, it's in the
component?
rest of the graph.
But why then in K? K
The
is the tournament.
tournaments, the sync component is in K. In K modifies component.
source component? Okay.
Ah. Oh, so off K, I get. Got it.
Okay, all right.
So I think maybe it will be easier if you just think of it as you're adding a minimum set of vertices to K so that the whole blob ends up being strongly connected. But it turns out, because of minimality, that would have to be a directed path from a sync component to a source component of K.
Oh, is it unique? Is sync component?
It is unique also because it is a tournament.
Uh-huh.
For the purposes of our proof, all we need is that it's a directed path and that it should be a shortest directed path between its endpoints. So I'm always going to denote closed tournaments as K union VP, where K will be understood to be a tournament of, and P will be a path. P will be this path, but and then we're going to say a vertex is a strong neighbor of a set of vertices if it has both an in neighbor and an out neighbor in a set. both an in neighbor and an out neighbor in X. And that lets us already define our dipolar set, and this is actually quite easy. So X is the set of strong neighbors of K union VP. Then the closed neighborhood of, I'm going to introduce some notation called C equals K union T of C union X is dipolar. And that's maybe mysterious, but actually it more or less follows from the definition pretty trivially. So remember C is K union X, so I'm going to draw this N C union X. So if this is your C, and these are the strong neighbors of C, so vertices that have both an in neighbor and an out neighbor in C. Then NC union X also has the neighbors of C that have just an in neighbor or just an out neighbor in C. So maybe these with just in neighbors and these with just out neighbors. And it also contains all neighbors of X. So I guess I'll just draw an edge without a direction to indicate they're neighbors of X. And clearly the neighbors of X that aren't neighbors of C and the neighbors of C that aren't in X are the only vertices of the closed neighborhood of C union X that can have edges to the rest of the graph, because we, for example, put the entire neighborhood of, because obviously like C's neighbors X are already in it, so C wouldn't have any vertex adjacent to C that is in X, wouldn't have a neighbor outside of N C union X.
Did you say that the neighbors of X are not neighbors of C?
No, the neighbors of X are the vertices that have both an in neighbor and an out neighbor in C. Right, I think it's hard for me to speak in words, so I need to. So if you're looking at the neighbors of C, and you're an X, you're not going to have a neighbor outside of S, because all the neighbors of X are already contained in S.
Yes.
So the only sets we need to worry about are these ones that I drew in red. So and then the fact that these can't be dipolar just basically follows from the definition. So for example, here some vertex has both an in neighbor and an out neighbor in the rest of the graph. Well, we know it has to have a neighbor in X because that's the definition. We don't know how this edge is oriented. And we know that every vertex in X has both an in neighbor and an out neighbor in C. So turns out that just no matter how we orient this central edge, we'll get a directed P4. So for example, if it's oriented this way, then can take the neighboring C4 and then just go this and this. And the same thing if we orient it the opposite way, we can take its out neighbor going out and go here and go here. And for the other case, it's also essentially the same thing. It's not a super enlightening proof. And it's also, I think, a part of why our proof is really only works for directed P4s. So
Then in order to make the proof work, we need to prove that there's a like minimum closed.
no, that just follows, because if you're strongly connected, you will have a minimal closed tournament, because you look at your look at a tournament,
Yeah. Right.
and then the whole, if that's not strongly connected, you can just keep adding vertices until you get something that's strongly connected. So you're asking me a question that requires me to write down and say the inductive hypothesis, but
I see.
it does in fact follow from the deductive hypothesis that you can
So
extend
you
the
start
graph.
with a single vertex tournament and then growing, or
No, I start with a tournament of maximum size. So I did not define this for the, because, oh, sorry, I missed an assumption. We need K to be a maximum size tournament. Where I'll use omega to indicate the size of a largest tournament in the graph. But that just exists because there's, there must be some largest tournament.
and this is a constant, right? Because you assume that maximum size tournament.
So yes, in the inductive hypothesis so I think it's perhaps time for me to state what, but I just will, since I'm almost out of time, we'll just sketch what the main, so this was the one main tool and this observation. I wanted to show that you get this easy close tournament. And then the second thing is, so for the inductive hypothesis, let me say, D is P4 free oriented. And then we'll let omega denote omega D. Suppose and then we'll choose, so basically we're assuming that everything, we have some digraph and we're assuming everything that's P4 free with smaller, the smaller clique number has a bounded dichromatic number. And we'll then show a bound that we can bound the dichromatic number of the graph itself in terms of this gamma, which is the maximum chromatic number of anything with a lower clique number than D, and the clique number of D. And this immediately gives us, since we're just trying to bound the dichromatic number of D, we can assume that D is strongly connected, and therefore it should have a minimum closed tournament with clique number omega D. And so that we'll choose that. We'll choose actually, in fact, for the P4 free case, we need a minimum closed tournament of clique number omega d, and then we bound the dichromatic number. And basically, the sticky part is so for I guess we don't really need. So for so we have K, and then we somehow have some path. Maybe it's doing something confusing, but it's going from a sink component to a source component. And so for the neighbors of K, we can just easily bound them because so K has size omega, so means n K, the dichromatic number of the digraph induced by its neighbors of K, has to have at most omega gamma, because for each vertex, it doesn't have a maximum size clique in its neighborhood. We can also kind of similarly do some easy tricks to bound the dichromatic number of X and its neighbors. And so the tricky part is to look at this path, and somehow we need to bound the dichromatic number of the neighbors of this path. But we can't use this trivial argument where we're like, okay, so trivially, if P is the path, the dichromatic number of NP is at most the size of P times gamma. But P might be arbitrarily long. We don't have any control over the size of P. So the main part of the proof was to kind of note that in a P4 free graph, there's a lot of structural restrictions on how edges can happen within the neighbors of P, and we can bound the dichromatic number of the neighbors in this way. And so that's what I just wanted to show the two main tools of this proof and kind of how this proof is limited to P4. So that's essentially the conclusion of my talk. I can mention, and I mean the open problems are pretty obvious because it's open for every tree that is not a path on at most 4 vertices or an oriented star. So I think maybe the more maybe subtractable cases would be maybe forms of P4 that are like brooms. So actually I would like to maybe do this one. And the reason I would suggest looking at these friends is because there's been some preliminary related results by Humpmore and Sturkle where they're excluding 2 of these kind of rooms, and then they get that it has a bounded dichromatic number in terms of the clique number. And also this one, it's still open whether or not excluding this bounds the chromatic number of the entire graph. And anecdotally, graphs that it seems like this maybe would be easier to get a bound on the dichromatic number if it's not obviously, if it doesn't obviously not bound the chromatic number. I don't think the conjecture is true, so counterexamples also would be great.
Okay, thank you. Right. Any questions? So what is the bound like? Is it like polynomial?
No, it's simply exponential. It's omega to the omega plus 7.5, I think.
What? Something like that? Oh.
Yeah, for some reason, I actually calculated these bounds. So for P4 free, we get omega plus 6 to the omega plus 7.5. For the alternating path, we get omega plus 7 to the omega plus 8.5. And for the other 2 orientations of P4, the like forward, forward, backwards, and the one that's flipping all of that, we get omega plus 3 to the omega plus 4.5. which is a asymptotically better bound than the trivial bound of than the dichromatic number bound that comes from the result of Chudnovsky, Scott, and Seymour.
Another question I have is like, you use this parameter omega for the induction, maybe. But what if you use the size of the largest acyclic tournament?
So that was all
the
the
two
stuff.
strands, yeah.
Oh,
That's
but that's equivalent.
equivalent,
because,
but maybe for induction it could be
maybe
it's harder to do
I
induction.
think. I mean, it's possible that somehow looking at doing the induction via doing induction on the size of the largest transitive tournament somehow gives you some other idea. The reason we didn't do that is because we really liked that you had the property that if you look in the neighborhood of a graph and of a single
Then-
vertex, then then the omega goes down by 1, and so we can just do induction on neighborhoods. Because really what we do in the entire proof are like, we can kind of choose a bounded number of vertices that dominate the entire graph, and then just give each of those vertices neighborhood a different color palette.
Okay. Any other questions? If not, let's thank the speaker.